Okay, cool. So, welcome everyone. This is Further Maths 923121. It's in the winter, October, November 2015. Okay, and let's scroll down to the first question. It is a statics question. Okay, so I don't know, people read out the question every time. Don't know if I want to read out the question every time.
They've all basically done the question.
Oh, okay,
so
yeah.
it's just like,
okay, so everyone knows the question.
Quick solution or
Yeah.
tips.
Pause now if you want to read the question. It says it's about a uniform ladder, it's length 3A, and there's a light inextensible rope coming from D to C, and
just crack on and solve.
Yeah, the important information really is that tan theta is 2 tan alpha. So those two angles they give you, that's really important information. So if I can write something down about that. Yeah, so let's scroll down. That's how I'd start the question, just by writing something down like that, because you know it's going to be really useful. So, oh, I don't really want to be there. Yeah, tan theta equals 2 tan alpha. Okay. And it wants the tension in the rope and the magnitude of the forces acting on the ladder at A and B. So that's what it wants. But it wants them in terms of the weight of this rod and alpha, the angle it gives. Okay, so you don't want theta, so you need to eliminate that at some stage. So there's 4 forces on this ladder. Okay, there's one at B here. It's a reaction force. So because this is smooth, there's no vertical component. It's only horizontal, like that. Okay. We also have halfway along the rod, because we assumed it's uniform, it says it's a uniform ladder. We have a weight force, which acts completely vertically downwards. And then here at C, we have a tension from the rope, which has to be acting inwards, because otherwise it doesn't really work for ropes. It would go slack otherwise. And then the final force we have is on the ground, which again it says is smooth. So that means it must be completely 90 degrees to the ground, okay? So there's only 4 forces on the system. And I'm not going to go through the in-depth maths, because it's quite tedious, but it boils down to 3 main things, really. Well, the main idea is it's static, so nothing's moving, okay? Which means that there's no net force. And also, because there's no movement. Oh, hello. Oh yeah, put that me. Also, because there's no movement means there's no net moment. Okay. Net moment. And we need to use those 2 facts to figure out what this force is. I said 3 facts at the start of this because really there's a vertical component of this force and there's a horizontal component. Okay, so vertically, we have that, if we just scroll up, we have B doesn't act vertically at all. We have the weight force, which I'll label W. I'll call this force at B, I'll call that F subscript B. We have a weight force here. We have the tension, which we'll call T, and we have FA here. So FB doesn't act vertically at all. We'll call the upwards direction positive. It's always important to define a direction. Oh, that's not very good. How do I delete? How do I? And then there we go. Okay. Yeah. So we'll call the upwards direction positive, which means that the weight is acting in the negative direction. So we have minus W plus this force FA, okay? But we also have some component of T. And in order to figure out what that component is, we need to figure out what angle this makes to the vertical. Okay? And I seem to remember figuring that out as, I think it's alpha plus, or this angle here is alpha plus theta. Did you figure this out as well? No, this angle is alpha plus theta. So once you figure that out, it's just a simple case of, ooh, how do I move this here? There we go. You want to take away T. Well, that's not very good. Pen's winding me up. Okay, there we go. There we go. And here. I want to take away t sine theta plus alpha. And that all should equal 0 because there's no net force. We can do the same for the horizontal, and we can do the same for the vertical. And then the other thing we need to do is take moments. So we need to take moments about B, D, and B, D, A, and C. And every time you take moments about one of those points, you eliminate a force. So when you do it around B, there's no moment of FB through B, so you lose the FB force. When you take moments about D or C, you lose any information about T because T doesn't have a moment about D or C. And it's the same when you do about A with FA. Once you do that, you get a system of equations, which you can then solve. One other trick you need to use really is you have sine theta plus alpha. That's the same as saying sine theta cos alpha plus cos theta sine alpha. Oh, well, let me write off here. Okay, fair enough. Get rid of that. And then what's that? It keeps moving. Okay, yeah. And then add on cos theta sine alpha. And then if you divide through by, or you bring out a factor of cos theta, tan theta, cos alpha, and then you add on sine alpha, and then you can use the fact that I wrote before that tan theta is 2 tan alpha, and oh dear me. Okay. Get rid of that. Okay. And then you get cos theta is 2 tan alpha. But I'm not going to write the tan alpha here because tan alpha is sine theta divided by cos, or tan alpha is sine alpha divided by cos alpha. So if I were to put a tan alpha in here, sine alpha divided by cos alpha, there's already a cos alpha here, so you can see those will cancel. And then add that to the sine alpha. And we can see that it's just going to be 3 cos theta sine alpha. Okay, that's the main trick to the question, really. Once you've got that, you can just take moments, solve for the vertical forces, and then just work through the question. You should be able to get the forces at A and B in terms of W and alpha only, okay? Okay, second question. You have always start with the diagram when you've got questions like these. It makes the whole thing a lot more simple. So you have a small uniform sphere A, I'll draw that here. It's got mass 2m. It's moving at speed u. Hello, okay, brilliant. On a smooth horizontal surface, when it collides directly with a small uniform sphere B of mass m, which is at rest. So I'll just draw that not moving now. Hello. The spheres have equal radii. All that means is that when they collide together, they're going to collide with their center of masses in line with each other, which means that all of the velocity of this will be in this sort of direction. It's not going to be like at a downwards angle or an upwards angle or something, which would be the case if they were different sizes. So that's a little point there, if that might have confused you. The spheres are equal radii, and the coefficient of restitution between them is E. Right, coefficient of restitution, what that means is just the ratio of the relative speeds after divided by the relative speed before. Okay, so this is before. This little diagram here is before. Let's draw an after diagram. So we have 2m, it's moving at some speed which you don't quite know. We'll call it, we'll draw all the speeds in the direction I've drawn them here. Doesn't really matter if they actually are going the other way. All we'll get is a negative sign if that is the case. We'll call this V A, V for final velocity, A because this is particle A, and then we'll then draw the other one, Oh, that's a bit. We'll then draw the other one. There we go. That sphere is not very good. VB. Okay, both in the same direction. Doesn't matter. If we get a negative sign, that means that we assume the wrong direction at the start, which isn't a problem. It wants expressions for the speeds A and B immediately after. All we have is E, so let's put them in terms of E. Well, we have E and U, so let's put them in terms of, well, and M. E, U, and M, okay? They're the only things we want the answer in. Right, so the way E is defined is that it's the relative speeds after divided by the relative speed before. So the relative speed after is VB minus VA, and the relative speed before is U. I'll just double check that. Oh, actually, do you know what? I should probably have put. Oh no, that's fine. Yeah, you have to be concerned sometimes about the sign of the direction. So I've done VB minus VA here, but if I had done VA minus VB, it would have been in the other direction, and that would have given us possibly a negative sign later. And using this information plus the conservation of momentum, we can't use anything concerning kinetic energy. Normally, you might be tempted to say, what's the kinetic energy before? What is the kinetic energy after? And equate those. But the coefficient of restitution here tells us that not all of the kinetic energy remains in the balls after the collision. Maybe some goes as heat or sound, so you can't use that. All you can use is conservation of momentum, okay? So before, the momentum is 2mu, because it's just that ball. Oh, dear me. Oh, let's just ignore that line. I don't want to delete the whole sphere. And then afterwards, so we'll equate that to afterwards, it's 2mVA plus mVB. We'll use these two equations to get the answers, which are in the mark scheme. I'm not going to do it. Some pretty easy maths, but that's the method. Don't use the kinetic energy before is the kinetic energy afterwards. That will give you the wrong answer. Okay. Subsequently, B collides with a vertical wall. So after the collision, it collides with a vertical wall. I'm drawing the wall here. That's a wall. I'll call E dash this coefficient of restitution, just so I don't want to put in a number every time we have to do an equation. After B has collided with this wall, the speeds A and B equal. Okay, so spoiler alert, the speed of A after the collision last time was, from the mark scheme, I think it was 2u over 3, 1 plus E. Is that what you got? Or was that for A? Was that for B? This is for B. Okay, yeah, sorry. I've read the wrong one. So this is B. Thank you for, oh, has it done that? Okay, I'll say that's B. That's, you know, that's terribly confusing. I don't mean not equal to. I mean is equal to. There we go. So this is the speed of B, and the speed of A was equal to 2 minus E over 3u. Is that right? Yeah. Cool. Okay, so that's the speed of A. So all you know is that this speed is equal to the speed of B after it hits this wall. So B is originally traveling at some velocity into the wall. After it hits, I'll just draw after it hits, it's moving in the opposite direction at VA. Okay, it has mass M still. And yeah, so now you just use the restitution formula thing again. So you've got E dash in this case is the ratio of B after the collision, which is VA, divided by before, which is VB. So you get VB, which is 2u1 plus the old E over 3. VB times E dash equals 2 minus E over 3. U. I believe that's right. Is that what you had when you did this? When you did this one? Or have I made an error? Let me just double check. Can't quite see my working. It might be hard. It might be hard for you to tell because no, I think that's right. And then you just E dash is 0.4 if you're wondering. That's what they're giving you in the question. Okay, I haven't put in the number because it makes everything a bit messy in my opinion. So if you work that through, I think you should get that E is 2/3 as it asks. And then for the last part, probably the hardest part. So it's probably best to draw this in 3 stages. So the first stage is that we have A. Why did it do that? Am I going too quickly? Okay, A is moving at VA. B is moving at VB. And it's before it hits the wall. In the second stage is A is still moving at VA. Oh. Let's get rid of that. Okay, A. Oh, why did you do that now? I'll slow down a bit. A. There we go. Still moving in the same direction with the same speed. But B is now moving. It's cheeky today. Maybe I'll stop drawing the spheres. I might just draw the letters if it keeps doing this. There we go, go on. I think it thinks I'm drawing straight lines. It's now moving at the same speed VA after it hit the wall. Okay? Okay, and how we do this problem is that we find how far A travels, because A's been moving the entire time B's been moving. We found how long A has been traveling in the time that it takes B to hit the wall. And after B has hit the wall, seeing as we know that they're moving at the same speed, we just know that the distance they're going to meet at is the middle between A and the wall. Okay? Okay, cool. And once you have that information, we can actually go through and figure it out, okay? But again, I'm not going to do that. I'm just going to skip straight through to 3, which is one of the harder questions. Oh, am I going to do 3 above here? Okay, I'll do 3 above because that's where the only space I have. Okay? Okay, so A and B are 2 fixed points on a smooth horizontal surface, okay? So let's draw that. I'll draw it up here. Okay. We know the distance between them. I don't really want to draw a lot of lines on here because I think it'll make everything quite confusing. Let me just get up my diagram. Okay. One end of a light elastic string of natural length A and modulus of elasticity M, mg newtons is attached to the point A. Okay, so we've got a string here, natural length A. So I'll call this string 1. It has what I'm going to call lambda. I don't know if you've been using the same symbol, but I'll call that for the modulus of elasticity, mg. And it has natural length, which I'll just call L1. I'll put a 1 here so you know which one I'm talking about. Natural length A. I don't put everything down yet. The other end of the string is attached to a particle P of mass M. So it tells you at some point P is in the middle. I'm just going to draw it now because I want to write it down. M, draw a little circle around it. Oh, it keeps doing that. Never mind. P. Okay, there's a second string, string 2. It has modulus of elasticity 2 mg, so it's twice as stiff, 2 mg newtons, and it has a natural length Ka or K. No, it's K. Where the natural length Ka. Sorry. Yep, that's right. And it's attached to B. Okay, so we've got these 2 strings coming in from 2 different directions. Given the system is in equilibrium when P is in the middle, the midpoint of AB, find the value of K. So both the strings are attaching onto P, and they're pulling. I've drawn the forces here. I drew this force wrong. Wait, I drew the forces the way they act on P, okay? So they're both trying to pull P towards them, but they can't because it's in equilibrium, okay? So equilibrium always means there's no net force. You might want to throw in Newton's second law. You might want to say that. Might give you marks on the exam. There's no net force. That's the main important thing. So now we need to know how to figure out the force from a string, and that is equal to the fractional change in the length multiplied by the modulus of elasticity. So we need to figure out the fractional change in length, and we already know the modulus of elasticity, and we need to equate these for both the strings, okay? So I'm just going to go ahead and do that in one step. So the force from string 1 is equal to the force from string 2. Okay, which implies that, okay, what's the fractional change in length for the string 1? Well, we know it's, sorry, the entire length between AB, which I probably should have written down, is 3A. So we know that it's 3A over 2 because it's stretched halfway between them. So that's how long it is now, over 2. We know its natural length is A, so it's normally A long. Dear me. Okay, so that's the change in length. The original length is A, and it has a modulus, dear me, mg. And for the other string, it has the same length. It's still stretched by the same amount, 3A over 2, but it had a length Ka originally over A. I've missed a 2mg in here. I might just get rid of this one and divide by a half because I ran out of space. Okay, so these are saying the same thing. Okay, we can divide through by the a's straight away. So we get 3/2 minus 1, which is just a half, multiplied by half, which is a quarter. On that side, I think. On the other side, we get 3 over 2. Sorry, I forgot K here. Its original length is K. Okay, tell me if you notice next time, because I do sometimes make mistakes like that. Thank you. And these both need a K, so sorry, that should actually be a 1. And there should be a K in the denominator. Does this look right now? This is what you had before? Or is there another mistake in there? You sure?
Yes.
Okay, good.
I think the left-hand side is 1/2.
You think this needs what, sorry?
It's the half rather than.
Oh yeah, so I did have, I think the half is supposed to be there because I've divided both sides by 2 quite early. So I think it was this, but I've divided by a half when I moved the 2 over to the other side. Does this look like what you have? Multiplying everything by 2? It doesn't. I know. Okay, maybe I've made a mistake here. Let me just go back. Hopefully we can find this because that'll slow us down quite a bit. I might be looking at a piece of rough working rather than. Oh, I'm missing another factor of a half, aren't I? 2g, 3 over 2, a. Yeah, this bit's right. A is here. I'll get rid of that. So I think this what's happened is I've tried to write this all down in one go, and I've run out of margin, and it's made me make an error. So I'll just go back a bit. Backtrack. 3 over 2 minus a mg equals the thing below it, 2mg. Oh my goodness gracious, this pen. There we go. Okay. 2. It's not quite registering fast enough. 2, yeah, mg over k. And in the bracket we have 3 over 2 a minus ka. This bit's right, isn't it? I think so too. And then let's do things maybe slower. 3/2 minus 1, because I've just got rid of the mg over a, equals 2 over k. So just double check. 3, 2, minus 1, blah, 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 mg, yeah, divided by mg over a, yeah, k, 3 over 2 minus k. So that gives us a half, yeah? and then we divide by the 2 from the other side, so that goes as a quarter, equals 3 over 2k minus 1. Is that right?
Yeah.
Okay, so this is right. I must have missed a half. I'm not really sure where it came from. Yeah, and if you solve all of this, you get, I think you get 5 over 6 is in? Or 6 over 5? 6 over 5. And go through, okay? Okay, so that should have been more painless, just a few algebraic mistakes, but k is 6 over 5, okay? Okay, now this bit is quite hard. I've sort of don't have enough. Oh, I've got loads of space up here. I didn't realize. Okay, so I'm going to do the next bit above here. Call it part 2. It says particle P is released from rest at a point between A and B, where both strings are taut. It hasn't told you where. It just wants you to show that it performs simple harmonic motion and state the period. Well, how do you even begin to do this? Well, what a good way of starting is to start with good old Newton's second law. Here's just a diagram just to refresh yourself, okay? So one string is pulling it this way, the other string is pulling it that way. We'll start with Newton's second law, which I guess you should know from mechanics. So Newton's second law is that F equals ma, which is the same as saying mx double dot. Okay? And what is x? That's a good question. We'll define x as a displacement of p towards b. We'll just call that the positive direction. We'll say that is x. So if you increase x a little bit, you've moved it a little bit towards b. If you make x negative, you moved it away from b towards a. Okay? So that's what we'll call x there. And we'll plot that into an equation. So we want to find the difference between the force at B. So in the positive direction, this way, we want to find the difference between the force exerted by the second string. I call it FB because it's pulling towards B. And the other one I'll call FA because it's the force from the string on A. So the difference between those forces gives the force in the direction of X. Okay? Let's write down what that is. So for FB, we have the general formula for a force by one of these strings. Is that. So we need the fractional change in length for FB. So normally B is 3a over 2 long when when P is in the middle. Okay, so we start off by writing 3a over 2. That's the length it's at. And if I move it towards B by x, it's not 3a over 2 away from the midpoint anymore. It's actually 3 over 2 minus x away, okay? Because this string was 3a over 2 long, but now I've moved it closer to B by x. It's now 3a over 2 minus x long. Its natural length, which I'm going to have to take away, was ka. I know we know what k is, but I don't want to put in numbers yet. And we need to divide that. Oh dear. Yep. Go on. That by the natural length, which is k a multiplied by 2 mg. And we need to take away then the force exerted by A, just because of the direction we define as positive. So likewise, A was 3a over 2 long. If we move the particle in the x direction, the string actually gets longer. So we need to add on x. So that's, just remember these two numbers here at the start, they represent how long the string is. And this second one represents its natural length, okay? So this is how long the string is if we move P a distance x. And then we then need to take away its original length, which is A, divided by A, and here's a modulus mg. Okay, so that's just writing down the force on the string. How do we show that simple harmonic motion? Well, we'll work through this, and I'm going to literally ignore all the terms apart from the ones with x in them, because they don't matter at all. So we'll get minus 2mg from this bit, and the minus from the x over ka minus mg, well, yep, I will write the mg. Mg, it's a minus because there's the minus sign out here and the x has a positive sign. So mg x over a plus a constant. And you'll see why the constant doesn't matter. I think if you figured out this constant, it would be 0, but you don't even need to figure it out at all. We know k is, I keep forgetting what it is. I should write down k is equal to 6 over 5. We'll use that information now. So 2 times 5 over 6 is 5/3. So this whole thing is minus 5mgx over 3a minus mgx over a plus c. Is that what I had? I think I got, if you just add those together, just double check my calculator. 5. Did you get this far?
Yeah.
Okay. Yeah, if you could just do these bits for me, because I've got awkward using a over 3. Yeah, you get 8 over 3 minus 8 over 3 mgx over a plus c. Okay, so now you have the force equals minus 8 over 3 mgx over a, but you also knew the force from Newton's equation was mx double dot. So the m's cancel, and you get x double dot equals minus 8 gx over 3a plus c. And now, magic lazy bit is that I didn't bother figuring out whether the constants, what they added to, because you can now change x to anything to get rid of this c. And because c is a constant, the derivative won't be changed at all. So this already shows that is simple harmonic motion. We have something in the form of x double dot equals minus omega squared x. That is simple harmonic motion, okay? We got rid of the c by saying that we can make a coordinate transformation of x to x dash. And in doing that, so we can choose this to get rid of c. This is probably more technical than you need to even know. You probably should just figure out the constants, but I couldn't be bothered. So x going to x dash would make x double dot going to, we'll say x dash plus c. And then that means x double dot is just x dash double dot. Because the c, when you differentiate the c, is nothing, okay? So we could have changed x to something that would make this c go away additively, and then if we then differentiate that thing, it would be put back into a simple harmonic form, okay? So we can just change the variables like that, and the c just goes away. Oh, I didn't mean to do that, but that worked out quite well. Okay, cool. The last step is just using these terms in front of the x dash. That is now the omega squared, is this 8g over 3a, I think. Don't know if that was in the mark scheme. Yeah, using those terms, it wants the, can't quite remember what it wants. Does it want the period? Yeah, it wants the period, okay? So if you take the square root, that gives you omega, and you know omega equals 2 pi over t, yeah? So take the square root of this, that gives you omega, and then you can rearrange the formula to get t, okay? And that should be the answer that they have in the mark scheme, I think. I think that was the end of the question. Yeah, okay, cool. There's one more part. I'll do that in the bottom bit. So in the case of P is released from rest at distance 0.2a from M, so draw A, draw B, here's M. It starts off a distance, call it A away, big capital A because it's the amplitude, but that's a bit of extra information. The speed, it tells you the speed when it's closer. We'll call that closer position X, 0.2 0.05a, and its speed we'll call v. Its speed is 0.7. And it wants a. Okay, so here's a little formula. I'm not sure if you're supposed to remember this or remember any formulas like this, but this one works quite well. Okay, so we start with x double dot equals minus omega squared x. Now x double dot is d2x by dt squared, but it's also dv by dt, isn't it? Because dx by dt is v. So if we differentiate x twice, this is doing the same thing. We can split this up into dv by dx using the chain rule times dx by dt. But what is dx by dt? That is just v. Okay? So we now have that equals, oh, I've moved on to my diagram a bit, minus omega squared x. So we have an equation that has just v's in it, dv's and v's, and x's and dx's in it. So if we actually integrate this whole thing with respect to dx, we should get an integral of v dv equals an integral of minus omega squared x dx. Just integrating both things with respect to x. Okay, so if you integrate this with respect to x, the dx goes away. If you integrate this with respect to x, you get this. Okay, and then solving that, we get v squared over 2 equals minus omega squared x squared over 2 plus c. Get rid of the 2's. I wish I had more space. I'm gonna move down here. Get rid of the 2's. I'm not going to change c because it's the same. You can just redefine it as a different constant. It doesn't matter. Nothing changes. Plus c. Okay. Now we need to find the c using the initial conditions. So we know the velocity is 0 when x equals the amplitude, which therefore gives that 0 equals minus omega squared plus c, which immediately shows that c is omega squared a squared. Okay, so that's the only thing that gives 0. And now using that information, we can find a, because we know v squared at a specific point. We know omega squared. I think we figured that out. We know the x squared value. And we have the a value to start with. The only thing we don't have is the a. So we just put in all the numbers. I think we get 0.7 squared equals, where did I write everything down? Did I do it on the back here? Yeah. Oh, I think I went ahead and rearranged everything. 0.7 squared, and then the period we had is 8g, well, the omega squared we had is 8ga over 3, I think. 3, we got that from above. Yeah, omega is the square root of 8g over 3a. So omega squared is 8g over 3, so it should be an a on the bottom. Yeah, so it should be an a on the bottom. My bad. And oh god, that messed up, didn't it? Oh, and it's come back. It's useful. Oh, it was 8g. Thank you so much. Over 3a. We know the x squared value. 0.05a squared. I think you see where I'm going with this. I could have factored out the omega squared. We have whatever the omega squared is, can't bother to write it down, and yeah, 0.28. So we've got a formula with all numbers in it apart from an a. So we just work that through, and then we can find a from that. Alternatively, you can keep the numbers in a bit more and then do it at the end, but it's all the same thing. You're all just solving for this a here. You're solving for that, okay? So once you work that through, you should get the answer. I think a is 0.49. That's what I've got written down here, okay? Cool. So let's now move on to 4. Yeah, we're just checking for time. Okay. Particle of mass m is attached to one end of a light inextensible string of length a. Okay. The other end of the string is attached to a fixed point O. So O, it's length A, yeah. P is hanging at rest vertically below O. Right, I've drawn that. Luckily, it's projected horizontally, so it's projected this way. At a speed we don't know, so that should be 90 degrees. It's horizontally. And it completes a vertical circle. Okay, so we know it goes all the way around in a perfect circle. This string is inextensible, so yeah, that all checks out. If it was extensible, then you know when it went round, the string would be longer here and it'd be shorter here, and it could never go in a circle. Okay, so that's all the inextensible bit means. In the subsequent motion, the speed of p when it's at its highest point is u. I'll just write that u highest point. I would draw it on, but I don't have that much space. I think you should always start the questions by drawing a nice diagram. Show the least possible value of u is the square root of ag. Okay, how you go about this? You would say that from your knowledge of circular motion, you can write down that a is v squared over r. And this acceleration, I'll write down the force version, mv squared over r, which is just Newton's second law. This force or this acceleration can be provided, through various mediums. So when the particle's at the bottom, the string is pulling it up with a tension. It's keeping it going in a circle. But when it gets to the top, we arrive in a situation where gravity is also pulling in the same direction that the string is pulling. So we can have that there is no tension in the string, and in fact, all the acceleration is coming from gravity. But what we can't have is that the acceleration that we need to go around in a circle is actually less than gravity. Because if it is, then before the particle even gets up there, it's going to fall down and the strings become slack, okay? So if the particle goes really, really quickly, it needs a really high acceleration, and that'll be fine. But the slower it gets and the slower acceleration it needs, all of a sudden there'll become a point where it doesn't need 10 meters per second acceleration to go in a circle. So gravity's too strong to keep it going around in circular motion. It's just going to drop off early, okay? So the condition is actually that to stop the string becoming slack, we'll put stop slack. That looks like a st. We need that the acceleration of the motion is greater than g. If it's less than g, then we're in a problem. We're not going to do circular motion. Another way of thinking about this is that the tension in the string at the top is mg. Sorry, I didn't want to write that. I mean the acceleration or the force, the centrifugal force is the mg plus the tension in the string. Okay, and we can't, if this drops below a certain amount, we can't lower gravity. So eventually we'll be required to get a point where the tension in the string is negative, but you can't have negative tension in the string. Okay, so that prevents that's an unphysical condition. Okay, so all we need is that the acceleration is greater than g. The acceleration is v squared over r. We need to be greater than g. The radius of motion is a, so we get u squared. Is u squared the value at the top? Yeah, u squared is the value at the top over a needs to be greater than g, which implies that, or equal to. It could be equal, which means there's absolutely no tension in the string, which means that u, oh whoopsie daisy, oh goodness. Let's go with that. U is greater than or equal to the square root of ag, which I think is exactly what they wanted, okay? So as long as you explain yourself by writing this, so that's the condition, you should get both the marks there. I think what they want you to do is something more like this and say the tension can't be negative. I think this is a more intuitive way of thinking about it. But if this makes more sense to you, then definitely do that. Okay, they now give you that u is this critical value. When p passes through the lowest point in its path, it collides with and coalesces with. So coalesces means it joins onto with a stationary particle of mass m equals a quarter, MO4. Find the speed of the combined particle immediately after the collision. Okay, So we just need to use bog standard conservation of momentum, but we don't know the speed at the bottom. So how we're going to do that is by using an energy consideration. I don't think I've ever heard anyone call it an energy consideration. Conservation of energy, yeah, that's the one. So the kinetic energy at the energy conserved at all points. So E at bottom is the same as the E at the top. Okay, so E at the bottom is a half, we'll call it V squared. I don't think we've used V in this question. A half, and the energy at the top is the kinetic plus the potential energy. So we'll say at the bottom, we'll define the bottom to be the point where it has no kinetic potential energy, because you always define potential energy wherever you want. So we'll say this is the place where it has none, which means that the difference, we'll just write in this kinetic energy, the difference in potential energy is just is to do with the distance between the 2 points. Okay, so it's a circle with radius a. So the height is 2a. So the potential energy is mg, the change in height. So plus mg. Oh, I'll just delete that. Didn't quite write slow enough there. mg times the height difference, which is 2a. Okay, so if we then go through that formula, I think we get V equals the square root of 5ag, or V squared equals 5ag. Yeah, okay, cool. Okay, so you've done this, that's good. So that's how we get the speed at the bottom, just an energy consideration. And then once we've got that, we just use conservation of momentum. So what did we call it? Speed at the bottom, V, I think. mv, that's the momentum for, equals m plus m over 4 times the new speed, which I don't want to V. Might call it S. I hope that doesn't come back to bite me. Call it S. Yeah, and then once you've got that, so this is just using momentum as mv. So this is the mass of the particle that's on the string. This is its velocity, and then this is the new mass. It's the old mass plus the new one because it coalesces together, and this is the new speed. So that means that we have that's 5m over 4. So when we multiply, we get 4 over 5m times m, and then put in our value for v. I think this is right. 4 over 5 square root 5ag. That's what S equals. Is that all I asked for? Yeah, find the speed of the particle. Okay, good. And then in the subsequent motion, when OP makes an angle theta with the upward vertical, the tension in the string is T. Find an expression for T. Okay, cool. So we'll draw a circle again. Actually, let's not bother drawing a circle. Let's just draw on the string. There we go. It makes an angle theta with the vertical. Yeah, and what's the expression for T in terms of mg and h? Cool, yeah, let's draw a free body diagram. We've sort of already got one. Okay, we'll draw on the tension. So this is just the string. Tension's like that. There's only two forces acting on this particle. mg, okay? And we're not going to resolve horizontally or vertically in this case. Instead, we are going to resolve radially. Okay, so this is a vertical line, and this is a vertical line. So we know that these angles are the same, so this is actually theta. So radially, radially, we have this. We'll write it in terms of the centrifugal force, okay? So we'll say this direction is positive. So the direction towards the center is positive, which makes a bit more sense in this case. So the tension is acting completely towards the center. The weight is not. It's got a component, mg cosine theta, I think. And that provides the mv squared over r. So that's just this centripetal force from the formula we used above, and then these are the forces that we've resolved. Oh, sorry, I've got to stop using an r. It is a. We've already been told what it is. Fantastic. And then if we work that through, I think we get the tension is 6/5 mg, just putting in what v squared is. So with it, I say this v squared is the speed of. Oh, we haven't figured out v squared yet, actually. No, I need to figure out what v squared is. Right, we're going to do the same thing we did before. We're going to do some sort of energy consideration. So we need to figure out what v squared is. So how we're going to do that is we're going to say that energy is constant. Energy is constant. So the energy at the bottom, 1/2 ms squared, is the energy at any point. We'll just use a general V now because we're on a different part of the question. Plus its potential energy, because as this particle goes around in a circle, it starts at the bottom with a lot of kinetic energy, and as it gets higher and higher, it loses kinetic energy, but it gains potential energy, so the entire energy is still constant. So all we need to do is figure out the distance it moves up, which might seem quite hard at first, but if you just observe that this length is A here, the length of the string is A. So if you want the projection of the string onto the vertical, you just need to do A cosine theta. Oh, dear me. So A cos theta is the projection. So now delta H is just this distance here, which is quite nice. So 1/2 ms squared put minus mg, just put the delta H on the side. So the delta H was A minus A cos theta, because we want to keep it positive. That equals 1/2 mv squared. Yep. Right, now if we work this through, I think we get v squared equals 16 a g over 5. Oh, g over 5 minus 2a g 1 minus cos theta. Let me just double check that's right. Yeah, I think that's right. That's just putting in my earlier value of s squared. I think that's okay. Okay, so now we have a value of v squared that we can put in here in the first equation, star in it. So that gives that t equals 6 mg over 5 plus 3 mg cos theta. That's our answer. Oh, I want to find the value of cos theta when the string becomes slack. String becomes slack at t equals 0. Really, it's slack at t less than or equals 0, because you can't have a negative tension in a string; it won't push back. So all we need to do is find when this equals 0, or is less than or equal to 0. So if you just do that, 6 mg over 5 equals minus. Why don't I have a minus sign in here? It's quite weird. Not quite sure, because when I did this earlier, I got cos theta as 2/3. But now it looks like I'm going to get a negative answer. I know 2/5 even. Oh God, my handwriting is quite bad. Just work through it and see maybe if I figure it out. Okay, so that's the tension. So we have 3 mg cos theta equals minus 6 m over 5 cos theta equals minus 5. Yeah, I got cos theta is minus 2 over 5. I'm just thinking about the shape of a cos theta. Cos theta is minus 2 over 5. Is it? That's the same value as cos theta is 2 over 5. Nah, it's not really. It's a slightly different angle. Part scheme does say 2 over 5, doesn't it? I'm not really sure what's gone wrong there. I've probably just forgotten something silly. Come back to that if I have any ideas. Should be cos theta is 2 over 5. For some reason, I've just when I've done it now. Yeah, we'll come back to that maybe if I have you gone through the maths? No. Okay, I wouldn't worry about it too much. As I say, it's probably just a sign error. Maybe when I was doing this step. I mean, that does make sense, doesn't it? If you get minus 2 over 5, because in this formula, where's my formula for t? When cos theta is minus 2 over 5, then that gives this bit being equal to 0. So if cos theta gets greater than or less than minus 2 over 5, then that should give an answer of 0. Just double. Yeah, I think that is the right answer, and I've just managed to convince myself that it should be 2 over 5, but I don't think that's true. But I'll double check that. Okay, cool. So we're done with all the mechanics stuff. We're now on the stat stuff. And it says there's 10 observations of a normal variable x. And it's given following data. So we've got the sum of all the values being 222.8. And we've got this thing here, which is the variance. It's the difference between an x value and the average, squaring that, and the sum of all those. And that's 4.12. And it wants a 95% confidence interval for the population mean. So first thing is always probably quite a good idea to do in these stats questions is to find the average. So what's the average? Well, it's just the sum of x divided by the number of thingies. I wish it would do that. Yeah, okay, we'll see. N. So it's 222.8 divided by 10 equals 22.28. And that's the mean. And now we need to estimate the standard deviation, okay? We don't know the standard deviation, we've just been given the variance. So if we want to figure that out, we know that we can use the formula. Standard deviation is the variance of x divided by n minus 1, because it's an estimation. This minus 1 is sort of pessimistic because if you divide it by n, the answer would be smaller. So n minus 1 makes the answer slightly bigger, and that's because we're doing an estimation. So we have 4.12 over n minus 1, which is 9, which should give us a squared value. I think it's 103 over 15. Do you want to do that quickly, just to check? It might be the square root of 103 over 15. I would like to be able to check as I go along. Nope. You put it in your calculator, just do 4.12 over 9 and just see what that pops out.
103 over 2.
Oh yeah, I must have just written down. I must have just written it down one. Well, if you do, why have I written down 15? If you just, so was it 225 on the bottom?
Yes.
Okay. I don't know where I got 15 from. Okay, so that gives us our standard deviation. And we're eventually going to end up using this formula here, so I'll write it down. The interval that we want is the mean minus a t star value, t star sigma, which is our standard deviation, over the square root of n. Oh my gosh, it's being not very sensitive here. Oh, what are you doing? I'm sorry, I'm trying to write square root of n, but the pen's not really working. There we go. That's not very clear, is it? I'll just start that again. Okay, cool. So yeah, sorry. So it's the average value of x minus t star sigma over the square root of n. And the other one is plus. So it's the same thing. Ugh, this part of the board isn't working very well. I'll just put a plus there. You know it's the same thing that goes in there. Okay. So we have our sigma value. We just need to figure out our t star value. So we'll just figure out the degrees of freedom first. So the degrees of freedom is the number of observations minus 1. So in that case, it's 10 minus 1, which gives us 9. Okay, that's the degrees of freedom. And then we need to figure out we need to use our confidence level to figure out what t star value to use. So in the tables, it comes with the t, a degrees of freedom, which I think is called a v, and then some sort of confidence value here. And the way we figure that out is by doing 1 plus the confidence it asks us, so 95% over 2. So we do 1 plus 0.95 over 2, that gives us 0.975. So now we know the value we need to look up is T9, because that's the degrees of freedom, plus this little, I called it an alpha value, I don't really know what it's called, plus this in the table. And if we go and look at that, that is a 2.262 T star value. Okay, and now that we have that, just the one last step to make the interval is to take the average, which is 22.28, take away the t star value, 2.262, which we just found in the table looking up under 9 and this. And then we multiply by the square root of that thing we just figured out. Oh, sorry, I forgot a square root here. Oh, no, I don't think I did. Never mind. I think that's why I put a 15 in at the bottom. I took the square root of 225. Whoops. Yep, and then we divide by the square root of the number of observations, which is square root of 10. Okay, let me just double check I put in all the right numbers here. 22.8. Sorry, 22.8. 0.28 even. Minus 2.262 times square root 103 over 225 over square root 10. And that gives you 21.796, which I think is the correct answer they put in the mark scheme. And then the other one, you get doing basically exactly the same thing. You get 20.7639. And just for a little bit of context, what this actually means is that this interval we've constructed, so I'll write it out more clearly, 21.796 to 22.763. I'll call that 4. I'll round up. This interval we've constructed has a 95% probability of containing the mean. Okay, that's all that confidence interval means. Okay, right.
Where does 2.26?
Oh yeah, sorry. It comes from the t star value. Okay, so to find the t star value, what we needed were the number of degrees of freedom, which is the number of observations, minus 1, which is 9. So now we know it's a T9 we need to look for. And then we need to get this number here. And how we get that number is by doing 1 plus the confidence, which was 0.95 divided by 2. So it gives you this. And we just look in the table on the formula booklet. So you look in the table formula booklet. Yeah, the T star value table. I'll get up here now. Not that one. Not that one. Was it that one? Yeah, it's this one. So T... 9 and then 0.975, 2.262. Yeah, so yeah, it's a bit of a kerfuffle. Okay, but we've got that now. I'll go through the stats one a bit more slow then. And now I'll just write down ready to start 6. I'll just get my little sheet of paper ready for 6. Can't find it. Oh, I started here. Cool. Okay, 6. This one's a little bit more, you have to think about it, apart from the start bit. So bias coin is tossed repeatedly until a head is obtained. The random variable x denotes the number of tosses required for a head to be obtained. So you keep throwing a coin, and then when you get a head, you stop, and then you write down how many throws it took you to get a head. And it's telling you that the mean of x, so the mean is equal to twice the variance. I wish I had a better symbol for variance, but I only use that. And yeah, so I couldn't really think of a nice way of explaining this. All I could do was go through the maths and find out a slightly more complicated. I feel like it might just be a formula they give you, but if you write down that the variance is the expected value of x squared minus the expected value of x squared. The expected value of the squared value of x minus the expected value of x, so the average, then squared. Okay, so one time the 2 is inside the bracket, one time the 2 is outside the bracket. That is the same as the expected value of x times x minus 1 minus the expected value of x minus the expected value of x squared. And the reason why that's true is because if you expand this out, you get x squared minus x, okay? And should that be a minus? Actually, I'm not quite sure. Hold on a sec. Should this be a positive then? A positive x? No. Okay, well, as I say, I couldn't really. All I was starting with the probability of getting an nth head is the probability of getting a head times 1 minus the probability you didn't get heads before. So say you keep flipping a coin and you eventually get a head on the nth throw. The probability that happens is the probability you didn't get one all the throws before that. So 1 minus p is the probability you didn't get one. So say I wanted to figure out what's the probability I get a head after 2 throws. Well, the first throw would have to be a failure, and that's 1 minus p. And the second one would have to be a success. So you see, if this is 2, then that gives me the same answer. And it's the same for if I wanted it for 3 throws. Well, the first 2 throws have to fail. So that's this. And then the next one has to succeed. So if you start with that, you can figure out using this sort of approach, you can figure out that this thing times x minus 1. You can figure out that is 2 times 1 minus p over p squared. And the way you do that is by just figuring out what the expected value is. So the expected value is the number of trial throws. Was you need to do a sum. This is why I really didn't like this question. I feel like there's a formula in your formula book that just gives you this result. That's where I should start. So equals 1 over p. The number of throws you expect to wait is 1 over the probability of getting a heads, and another one is that the variance equals 1 minus p over p squared. So these are the 2 results you need, because once you have them, you essentially get that 1 over p equals 2 times 1 minus p over p squared. But the only thing is that getting these results, I think, is way beyond what A-level further maths expects you to do. So I'm not sure if you are supposed to do something like this, or whether it might be a bit too much. But if you did have to do it this way to figure out this expected value, you would have to do this sum. So from n equals 1 to infinity, n times n minus 1, p times 1 minus p to the n minus 1. That's the expected value of x times x minus 1, because this is x, this is x minus 1, and then these are the amount of times they occur. So if you did that sum, you would then get this value. Is that right? No, you'd get this one, and then you can then use the expected value of x and the expected value of x squared to get this variance thing. I'm actually not quite sure how you do this one. If you have to do the maths, if I find out later you have to do the maths, I will go through this again because it's a really hard approach, but I feel like there's just a formula in the formula book. But we can go over that later. But for the next part of the question is way easier. You want to find the probability that it takes 4 throws for you to get ahead. Okay. And that's really simple. How do you get 4 heads? Well, you have to not get heads 3 times. Okay. And then on the 4th one, you have to get ahead. That's what it is. By the way, this earlier bit gives you p equals 2/3. Okay, so it's slightly more likely to get ahead. And if you just plug in those numbers, 2/3, 1 minus 2/3 cubed, that gives you 2/81. So that's the probability you get you get heads on x equals 4 after 4 ones. Okay, so now what's the probability that you get heads after 4 throws? Okay, you could, if you had an infinite amount of time, just be like, oh, what's the probability that it happens after 4 times? What's the probability it happens after 5 times? Yada, yada, yada. But this is really the same as the probability, 1 minus the probability that x is less than 3. That makes sense? So this is, what's the probability that you have to wait longer than 4 throws to get ahead? Well, it's 1 minus the probability you have to wait 3 or less. Okay? Because if you have to wait longer than 4, you definitely didn't have to wait sooner than 3. Okay? And this is much easier to figure out because there's only 3 things to put in. So there's 1 minus, this is the probability you get ahead straight away. Then this is the probability you get ahead after 2 throws. Then this is a probability, oh sorry, this one quick thing here. This shouldn't be a 3, sorry. This sign here is greater than 4, which means that 4 isn't greater than 4. Okay. So if you had to wait longer to get a 4, you definitely didn't have to wait longer than to get a 1, or this is to get it after 2 times. This is to get it after 3 times, and then this is to get it after 4 times. Okay, so 1 minus this probability, which is the probability you get it in the first 4 goes, turns out to be 1/81. So it's half as likely as the previous one. Okay, oh, it's down here, isn't it? And this one is, what is the smallest number so that the number of times you have to wait to get heads, less than that number, is greater than 0.999. Right. How would we go about figuring this one out? Well, the probability that x is less than or equal to n is the sum from 1 to n. So this is what we were doing before. We were just summing stuff, but now we have to do it more generally. So you have to do it for n. Is the probability that it doesn't become a head in all the n-1 throws times by the probability it does on the nth throw. So this is the probability that the number of throws you have to do is less than n. Okay. Yeah, and so now we just need to figure out a way of figuring out that sum. Okay. So how do we figure out this sum? Well, if we look at this sum, we'll call it S of P. The sum, it looks like a P plus a P times a 1 minus a P plus a P times a 1 minus a P squared. That means if we multiply it by P, do we want to multiply it by P? We want to multiply it by 1 minus P, don't we? Okay, so we're multiplying the sum by 1 minus P. We get a P times 1 minus P plus a p times a 1 minus p squared. Okay, so this term gets a 1 minus p, this term gets another 1 minus p, yada, yada, yada. The last term becomes p times, instead of 1 minus p to the n minus 1, it just becomes 1 minus p. Okay, so it's a geometric series. Okay, so now if we take these two away from each other, these two series, so we will subtract, we get an SP minus 1 minus p times SP equals p minus p times 1 minus p to the n. Okay, so we want to solve for SP, and if you work through the algebra, you get SP equals 1 minus p to the n. I'm pretty sure. Once you go through everything, because I think this what does this come out to me? SP minus 1 plus p SP. Wait, does that work? If I factor, oh, this should be an SP. Yeah. So sorry, these two SPs cancel. So you just get a PSP, and on the other side you get a P, and they just cancel out. So you do end up with this thing at the bottom. So that gives you how to do the sum. And yeah, so you then just use that formula. This sum needs to be greater than, so 1 minus p to the n. This needs to be greater than 0.999, it said in the question. Okay, so we can just solve through. So we need 1 minus 0.999 is greater than 1 minus p to the n. So log base 1 minus p. So the number you need to raise 1 minus p to in order to get 0.001 is n. We put that in a calculator, and then we get n equals 6.28. Okay, so we need n to at least be 6.28 so that the probability that x is less than n is greater than that. So what this really is trying to say is that if n is 6.28, it's really, really, really unlikely that x is going to need to be bigger than it for you to get ahead. But seeing as n, these are all integers, you can't have 6.28 throws. We need to round up to the nearest number. So n needs to equal 7, so that the probability that you only have to wait 7 throws is this. Okay, so that's what that question is. So it's a bit of geometric series and a bit of thinking, but otherwise than that, it's not too bad. Okay, and I don't really have much space for 7 at all. How about I just try and do it around the page. Okay, let me just get out my piece of paper for 7. Right, so continuous random variable has a probability density function given by this. Random variable y is, okay, so y is x squared, that's important. And you need to find the probability density function for y. How do we do that? An easy way to do it is just find the cumulative probability function. So the cumulative probability function is, this is just the probability density function is just when you take f of x multiplied by dx, that's the probability it's in a range. The cumulative probability distribution is if this was big f of x dx, that's the probability of getting everything in this range. Okay, so that means that in order to get the cumulative one, we need to integrate the probability density function. Okay, so we want it as a function of x. So we need to do an integral between 1, because it's a lower bound, 1 and x, of f of, call it x dash, because we can't integrate with respect to the same variable in there. So that should give us the cumulative probability function. So yeah, we just doing this integral. 1 over 21 x dash squared dx dash, which gives us, sorry, this dash isn't the derivative, this is just saying it's a different x to the one before. And when you do that through, that gives you 1 over 63 times x cubed minus 1. And then the other one, sorry, not what other one? Or now we now know, because there's a one-to-one correspondence between the x and the y values. So this is x, this is y. So when x is 1 and 4, y is 1 and 16. So it sort of curves up like that. We know there's a one-to-one correspondence between each value. So that means for the cumulative probability functions, the probability that x is a number between 1 and 2 is the same as the probability that this is a number between 1 and 4, because y is x squared. So we can now use that information to just put in here, well, y is x squared, so x equals square root of y. So to get the cumulative density function for y, so big G of y, we just put that in the same one for x, because there's a one-to-one correspondence, and it's quite easy. So square root of y, I'll call it y to the 3 over 2 minus 1. Okay? And now, to get back to the g of y is just the derivative of big G of y, which is multiplied by the 3, so over 2 times 63. That's y to the power of 1/2. I think that gives you, so this is a 2 and then a 1. Yeah, so this is 1 over 42 times y to the half. Okay? Now, we need to find the median value of y. And the way to do that is to find where the cumulative probability distribution equals 1/2. So y, median value means the value for which 50%, all the ones below it have a 50% chance, and all the ones above it have a 50% chance of occurring. So it's the middle y's in terms of the probability. So if we find the g of y value that gives us 1/2, that should give us the median. Why am I trying to figure out the expected value here? Yeah, so we just rearrange this and we say 1 over 63 y to the 3 over 2 minus 1 equals 1/2. Y equals 2 over 3. And could you just check that for me? 184? 10.2 something. Why have I got 63? Is that when I do it, I get a slightly different answer, but it's not that different. Oh, dear me. Let me just go through this quick.
This one is 10 point.
Yeah. I think that's okay. I think that's what the answer should be. Is that what's in the mark scheme?
Yes.
I think so. Okay, cool. So yeah, so that's how you get that answer. You just set the cumulative probability density distribution to 1/2, and then you figure out the y value that corresponds to. And for the expected value of y is just the integral over the range, so from 1 to 16, of y times by the probability of getting y, which is gy dy. Okay? So what you need to do for that is you need to do this integral. Oh, probably go a little bit faster because otherwise we're going to run out of time. Where's the integral? 1 over 42 y to the power of 3 over 2, I think.
Yes.
So over 2 dy. And if you do that integral, I think I got 341 over 35 or 9.74. I don't know if that's what. Yep. Okay, cool. So we know how to do that one. Great. Okay. We'll do these two. I don't know how long the last one's going to take us. Did you do the last one? quite a hefty one. Okay, maybe we can just go over that after this, because I don't want to make this one too long. We'll just do 8 quickly. So I think 8's quite a fast one. I'll just go through how to do 8 then. Also, where is my? Whoops, I misplaced my sheet for 8. Oh, is this it? Yeah. Okay. So the number of goals scored by a certain football team was recorded of each of 100 matches, and the results are summarized in the following table. So we want to fit a Poisson distribution to the data. So for Poisson distributions, they're characterized by having an e to the lambda. I can just borrow the formula for a second. Is it a minus lambda or? It's in here. Oh, is it not in here? It might not be in here. Oh, I think I've got it here. Right, it's e to the minus lambda to the r over r factorial. Okay. Also multiply that by the mean. If you don't want it, if you want it, not the mean, by the number of occurrences. If you want everything to come out as a probability. And so the first thing we should do, also another point is the variance and the mean are the same, and we just denote that by lambda. So what we want to do is to figure out the mean. So we just do 0 times 12 plus 1 times 16 plus 2 times 31, all of that, all the way up over the sum, which should be 100. And we get a mean of 11 over 5. So that's the mean number of goals, okay, which is 2.2. Okay, so the null hypothesis is that data is fit by Poisson. And in order for that to be true, when we now put the data into this form, we should get all the probabilities out in the same way, okay? So we'll figure out the probability of having 0 goals, which should be e to the minus 11 over 5 times 11 over 5 to the power of 0 over 0 factorial, which is just 1. And that gives us 11.080. Okay, and we keep doing that for all of them. We keep just figuring out what the probabilities are and spit them back out. So P1 equals 24.377. P2 equals 26.814. P3, we keep going. I'm going to write them all down. 19 for P4 equals this. These last two are sort of interesting. P5 is 4.759, and then P6 we get from doing 100 minus the rest of them. So that gives us a stupid answer. And we get 491. Okay, fantastic. Your exam board doesn't like this. They want you to combine bins if the expected value of the probability is less than 5. So here, the expected value of the probability is less than 5. So we need to combine the 6 and the 5 bin. So instead of having 6 or more, we're now going to have like 5 or more. 5 or more, because this bin doesn't help us at all. So now we have a P. So this is greater than 6. So now we only have a P greater than 5. And that has a value of expected value of 7.2 just by adding the just by adding the 1 for 5 and 1 for 6. Okay, 7.25. So don't forget to reduce the size of the bins. They get really annoyed about it. Okay, and the next bit to do is do a chi-squared test. So how do we do a chi-squared test? We take the sum of the actual value, which is called O, minus expected value squared, all divided by the expected value. So chi-squared is going to look something like, it's going to be the observed one, and that's why it's an O. So we saw 12 no goals, but we predicted 11.080. that should be a 1, 11.08. So we do that, and we add on, we observe 16 goals, then we actually predicted having, wait, did I write down this number wrong? Yeah, no, everything's good, right? Yeah, we actually predicted 24.377, and we square that. We divide by 24.377, and we keep doing that. And then we eventually get a chi-squared value of 7.99. Okay, so that's just what you get when you do this for every single bit of data. And then what we now need to do to finish the chi-square test is to go and check the table. So we run along, we go and check that. We have 4 degrees of freedom. And so we run along to our table. We look at the chi-square value, and the chi-square value is 9.488. Okay, and so now because our chi-square value is less than the accepted one, don't forget to look. We're looking for a confidence of 97 and 95% on the table. Took 4 degrees of freedom. The tabular value is greater than recorded, so it does fit. It does fit. Okay. Cool. I hope you got all that. Did you get all that down? Okay, good. And then we'll just try and do this one quickly, and then we're going to go through the other questions later. Cool. So this is bivariant data. We have 8 students. They sit in maths and French exams. The marks in maths are given by X, and the French marks given by Y, and they're giving you all this data, and they want you to know another student's got 72 in his maths. What do you think he should get in his French examination? And so how we're going to do that is we're going to say that we have got a scattergram. If we plotted all this data, X and Y, and there's just random, well, not random, but there's dots on this page, and we're going to assume a correlation between them and try and find a Y value given that we have an X value. So we're looking to fit a line on this data, a line on this data that has some value A and some value B, and these should be able to tell us who's got what results on what. Okay, and how we get the B value is by looking at the SXY over the SXX. So the SXY it's the sum of the X values times the Y values minus the sum of the X values multiplied by the Y values, sum of the Y values. Okay, so this is a lot of just formula stuff. I'm divided by the number of students. The SXX value is the sum of the squares of the X values minus the sum of the X values squared. Over N. And so you just use these values they've given you here. Make sure you divide by 8, not 9. There's only 8 students. The 9th student doesn't have any data yet. That's what you're trying to figure out. And so yeah, you figure out the SXY and the SXX values, and then you get B by taking the ratio, and you should get something like 0.608. And then you want to figure out A. A is much easier to figure out because you can sort of just look at it and be like, well, if I average everything here, then I just get A by doing that. So once you have B, A is really easy to get. We have the sum of the Y values and the sum of the X values, so we just need to divide by 8 to get the averages and plug those in. So then we get sum of the Y values, 400 over 8 minus 0.608 times the X1, which is 427. So people did better in maths. Cool. And that gives an A value of 14.128. And you literally just use the formula that we started with, this one that we assumed with the linear correlation, and you go, what was the A? Cool. Plus the B. Nice. And then multiplied by his value, which he got 72. Hey, almost done. Almost done. And that gives you 57.904. And you can't have 57.904, so let's round it up and give him 58. You could have done this the other way around. You could have done this by saying that x equals c plus dy and figured out the c and the d in the exact same way, and that would give you a slightly different answer. I think it's a slightly higher answer. So this is more generous, but this way isn't wrong. Yeah, cool. And then you need to test at the 5% significance value whether or not there is non-zero correlation between marks in maths and marks in French. So we probably should have done this first before we figured out what his mark was, but it's at the end of the question. So this is figuring out whether there is actually a correlation to a 5% significance. And the way we're going to do this is they have a really, really massive formula. It's in the formula bucket. Do you have it on you by any chance? Formula bucket. It's something like, I think I must have written it down at some point. R equals, just check it here, I'll figure it out. Yeah, it's more that way. Here, it's here. So R equals, goodness, it's the sum of the product of the x and the y values minus the sum of the x values times by the sum of the y values divided by n, just the top bit, and then you divide the entire numerator by the square root of ex squared, expected, oh sorry, that's not the expected value of x squared, that is just the sum of the x squared values. Okay, I mean, it all boils down to we're using this crazy formula, so you don't need to worry specifically about what I'm doing here, but I want to write it down for completeness. So that's one part of the bracket. I'll write another square root because I don't want to put in brackets. Sum of y squared minus the sum of the y all squared over n, because that's the other one. And you have all the numbers up there, thanks. You have all the numbers up here. So you just plug them all in and you get an R value of 0.797. Okay, which is great. And you also have, sorry, one more time. There's another table to look at that I forgot about. You have to go to the PMCC table. You know that your sample has 8 people. You can't include the result you just made because he didn't actually sit the French exam, where you weren't given his data, so you can't put that in. And this is a one-tail distribution, so you go along on your one-tail column, you look for 5% significance, you go down to 8, and you should get 7.07. Sorry, did I say one-tail? I meant two-tail. That's a two-tail distribution. Yeah, so you go down and it's 0.707. 707. Okay, and because your R value, R indicates how strongly correlated they are, so your R value was 797, which is greater than 0.707. So yeah, there is 5% significance between the data. Okay, so non-zero correlation. Cool. Okay, I think that's all we have time for. We can do this one in our own time. Okay, how do I end this? Stop sharing, yeah? Oh.